Ladies and gentlemen, the 2022 International Conference on Quantum Cryptography will commence in 3 minutes. Please kindly take your seats. And for audience who join us online, please get ready for the whole day conference. Thank you. Good morning, ladies and gentlemen on site here in Taipei, Taiwan, and also good morning to the audience online, and good morning to our session chair and our speakers online. Welcome to the 2022 International Conference on Quantum Cryptography. I'm your MC today again. My name is Rebecca. Welcome to day 3 of the conference, and hope you're ready for the whole day of fruitful sessions. In the very beginning, we will have an invited talk, and right now we'd like to welcome our session chair, Professor Jiahui. Welcome.
Oh, hello.
Hello.
Yeah.
So I'll give the floor to you.
Okay. Yeah. So good morning. So welcome to the Wednesday morning session for the invited talk of QCrypt 2022. And I'm Jiahui. I will be chairing the session from Houston this time. And there will be a Q&A time after the talk for you to ask questions. For local audience, you can just raise your hand in the Q&A time. And for online audience, you can put your questions in the Q&A box or raise your hands in the Zoom, and I will unmute you to ask questions. And today, it is my pleasure to introduce Jiahui Liu. She is a PhD student at UT Austin, supervised by Scott Aronson, and she's an outstanding young researcher in classical and quantum cryptography. In recent years, she published many nice results about quantum money, quantum copy protection, unclonable crypto, and the position-based crypto, and more. And today, she will tell us about her exciting work. And now, Jiahui, it is all yours. Yeah.
Okay, let me try to do the screen share.
Yeah.
I think I'm not made a co-host. I think the host has to issue me
the
yeah.
sharing screen. Yeah.
You just did. Can you try it again, please? Thank you.
Okay, I think it works now.
Mm-hmm. Yeah, that's good.
Okay. All right. So you guys can see the full screen of the slides, right?
Yes, I can see that.
Okay.
Mm-hmm.
Good. Okay. Let's start. Uh, so hi everyone. I'm Jiahui. I'm from University of Texas at Austin, and today I will talk about quantum copy protection and unclonable quantum cryptography. And this will be mainly based on the following works: new approaches for copy protection and hidden codes applications to unclonable cryptography. They were published in Crypto last year, and they were also at TQC and QIP. And this is joint works with Scott Arison, Chipeng Liu, Mark Gentry, as well Richard Zhang, as well as Andrea Coladangelo in the other work. Okay, so as we know, probably the most famous tasks that can be performed by quantum computers is to break many hard math problems widely used in modern day cryptography, right? Like factoring or discrete log, while they are believed to be hard on average for classical computers, and that's what most of the public key cryptography is relied on. There exists very efficient quantum algorithms, namely Shor's algorithm, to solve them. But on the other hand, as we go from the classical information world to studying quantum information, some properties of quantum information can also lead to new cryptography capabilities. Here are some famous examples of cryptography protocols based on quantum information. For example, the BB84 quantum key distribution protocol. Here, the two parties can share a classical secret while sending quantum information. And this can be achieved information theoretically. And some other examples include quantum money and quantum position verification. And these examples I listed here, their security has a close relationship with a quantum mechanics principle called the no cloning principle. The no cloning principle says that when given one copy of an arbitrary unknown quantum state, by no I mean we don't know its classical description, otherwise it's easy to generate copies. So it is impossible in such a case to generate two states same as the original one. And the procedure is just nonlinear and generally not allowed by quantum mechanics. And sorry, I think I just skipped a few slides. Okay, so this property has been applied in quantum cryptography, as mentioned before. One example is quantum money that was put forward by Wisner in the 60s. It was a pioneering idea which actually inspired the quantum key distribution protocol. So the famous BB84 state can also be called Wisner state because it was Wisner who actually brought up them at first and to use them to build quantum money. So what's quantum money? In a quantum money scheme, a bank can issue a money state to a user. A money state encodes a money value and also a serial number. A valid money state can get verified by the bank. When you hand the money state and the serial number to the bank, it will say, okay, it's a valid money state or not. So, but a malicious user, if it possesses one copy of the money state, it should not be able to produce two copies that can both pass verification. So this is something Wisner built, and we want to go beyond quantum money. We would like to ask whether we can leverage the unclonability of quantum information to encode even more complicated classical information. So Arison in 2009 put forward quantum copy protection. A company wants to sell a piece of software, for example, and we can see this software as a classical function. So for now, throughout my talk, when we talk about copy protection functionalities, we talk about a classical functionality. For example, it's used to decrypt, or it's like a game that you run on your laptop. So the software, of course, the company doesn't want the malicious users to pirate the functions. Otherwise, these pirate would just sell the copies cheaper, and the company could go broke. So they run this copy protection algorithm that turns this function into a quantum state, and they give this state to the user. Now the user can use this quantum state to run the same functionality. It would obtain the same evaluation result as you would with the original function f. But if the user wants to pirate the function, let's say let's say it just wants to split it into two copies, so that these two freeloaders, when receiving the pirate copies, they can both recover the functionalities. What we want is that a polynomial time adversary should not be able to turn one copy of this copy protected state into two copies, so that they both compute the function correctly. So of course, you may wonder why don't classical people care about copy protection, or like the patent protection? Of course they do. In modern classical cryptography, cryptographers care about copy protecting softwares and patents. And the way they do it is by obfuscation and watermarking. There are some other tools as well, but these are the major tools. Obfuscation is a cryptography tool that you use to scramble a program. When we receive a scrambled program, we can run it correctly. But when we look into the code, you don't know what the code is doing. And there's another tool that we call watermarking. So a watermarking is a procedure where you can just embed a watermark into a software, into a function, so that if someone tries to remove this watermark, it would break the functionality. But however, classical information can always be copied. The pirate can just take the whole obfuscated or watermark program, copy it, and sell it to others. So these tools, they don't prevent piracy inherently. But looking forward, we'll see that these classical cryptography tools that will be very important building blocks when we try to realize quantum copy protection. So now let's take a look at a slightly more formal definition of copy protection. There's a setup algorithm that generates a secret key. This one is not is optional. You can just combine it with the second algorithm called generate. So the generate takes in the function f, a classical description of it, and it also takes in the secret, and it outputs a quantum program, psi f, and this will be the copy protected program. So this quantum state could actually also contain some other classical information. For example, instructions on the user, instruction for the user on how to run the program, like a description of this quantum circuit. But for the simplicity of notation, we will just write the entire program in one quantum state. And the eval algorithm, basically it takes in the quantum program and the input and just evaluating it using a universal circuit. It outputs a computation result and a remaining state. So this eval algorithm is in fact also optional, because here I'm just describing it as running a universal circuit, so that actually you don't need a specific algorithm at all. But I'm mentioning this algorithm because I would briefly mention some other notions of copy protection at the very end. So for firstly, we need correctness. So for correctness of the scheme, we want the evaluation on almost all inputs to be correct. Here I'm just, for simplicity, writing it as evaluating all inputs correctly with probability 1, but of course with quantum, there's always a bit of error. And we also want the program to be polynomially many times reusable. And this reusability actually follows from the correctness of this scheme. And in particular, it follows when the function f is deterministic. So So this follows from the gentle measurement lemma, which says that if we can evaluate correctly with almost 1 probability, we can recover to the original quantum state with almost 1 probability, so that we can run it again and again. So next, we define anti-piracy. That is the most important property here. So in an anti-piracy security game, a quantum polynomial time adversary is given 1 copy of the authentic program. Oh, sorry. Then it also then it tries to produce 2 parallel programs. It wins if both of these programs evaluate the function correctly with a large enough probability. And we want any quantum polytime adversary to win with only negligible probability. Next, we take a brief look at a line of works on copy protection. So first, it was Ericsson 2009 scheme, which is for all unlearnable functions using a quantum oracle. And we will get to what unlearnable and the quantum oracle means later on. And in the 2 works we will mainly talk about today, the first one, we build it for all unlearnable functions using a classical oracle. And in the second one, we get rid of oracles and build copy protection for specific functionalities, which are here signatures, decryption, and PRFs, and in the plain model. And there is also another line of works that copy protect a simpler class of functions called point functions, and its extension called compute and compare. And they work in the quantum random oracle model. We will mention them briefly later. Let's first get to this very first result. So in 2009, Ericsson put forward the notion for copy protection, and he also gave the first copy protection construction for any unlearnable functions. So what is unlearnable? So learnable functions, let's talk about what's a learnable function. So learnable functions are functions that can be learned through its input and output behavior. So if you give this oracle to a quantum adversary, and it can just query the oracle for polynomial many times and produce a state or like a circuit that computes the function on a large enough enough probability of being right, then we say it alerts the functionality F. So we don't want to copy protect such functions, because if you imagine we give out a copy protection program, then the adversary could just run the program on a few inputs, and then it just produce another circuit that compute the same functionality. And no matter what we do with this copy protection, the adversary can always learn the function by just running it. Therefore, we only care about copy protecting unlearnable functions. So basically, Ericsson's scheme, it copy protects or possibly copy protectable functions. But there's one important drawback, is that it requires using a quantum oracle. So what is a quantum oracle? When we say quantum oracle, we mean oracles that implement functionalities of quantum circuits. And they can only be accessed as a black box. And they can also be, so in the words of cryptography, they can be implemented by something called virtual black box obfuscation. We normally call it VBB for short. And virtual black box obfuscation is an obfuscation tool that scrambles a program so bad, or say so good, and make it no different from accessing an oracle in the view of the adversary. So this is something very ideal. On the other hand, we have something slightly more practical. We call classical oracles. They are just oracles that implement only functionalities of classical circuits. But in the quantum world, they can also be queried in superposition by the adversary. And we can also say we can implement any classical oracle using a VBB obfuscation for classical circuits. So even though both VBB obfuscation for quantum circuits and for classical circuits are actually quite strong assumptions, quantum VBB is yet stronger So up to now, there is no known VBB constructions for any quantum circuit. And normally in the literature of, for example, computational complexity, when people show results, quantum oracles are also always considered as a stronger tool than the classical oracles. Therefore, Erickson asked the question, so whether we can build copy protection using only a classical oracle. Then in the first part of the talk today, we will show how to construct copy protection using only classical oracles. Before going to our classical oracle construction, we take a high-level look at Scott Erickson's quantum oracle construction. So the oracle basically takes in a quantum state and a classical input X, which is the input you want to evaluate. And the oracle checks if the state is the correct state corresponding to some secret embedded inside the oracle. And if yes, it outputs the evaluation. Otherwise, it outputs fault, meaning nothing. So such a verification procedure for this quantum state needs to be a quantum circuit. So our program needs to have a quantum state, but we want to verify it using only a classical circuit. So we want to realize a similar idea to Erickson's 2009 scheme, but using a classical oracles. Therefore, we need a quantum state that's verifiable using only classical circuits. And it also needs to be unclonable. What shall we do? The starting idea is to use the public quantum money scheme in Erickson and Cristiano's 2012 paper, something called hidden subspace. So a hidden subspace A is a secret subspace randomly chosen by the vendor of the program, for example. And it has exponentially many vectors inside, but it's still exponentially small compared to the full space. For example, it's a lambda, so the full space is lambda dimensional vector space over finite field of 2, and the lambda is a security parameter. Then the subspace state then the subspace is a lambda over 2 dimensional randomly chosen secret subspace. A subspace state is basically just an equal superposition of all elements in A. And the subspace states have the following properties. If we do a quantum Fourier transform to the state, we will go to its due subspace with all the vectors in A perp. And moreover, we consider the following hard problem. When we give a quantum adversary one copy of state A and access to membership oracles OA and OA perp, and these membership oracles have the functionalities that when I input a classical vector into the oracle and it outputs 0, saying that it's not a vector in the subspace embedded inside, and it outputs 1 if the vector is a non-zero vector in the subspace A. So we have these two membership check oracles for A and its due subspace A perp, respectively. And the quantum adversary bounded polynomially inquiries should not be able to output 2 vectors, one in A and the other in A perp. And of course, they need to be non-zero in order for the problem to be non-trivial. And this is a probably secure lower bound in the paper by Ben-David and Satas in 2016. And we will our security will rely on this probably hard problem. So the next question is, now we have these 2 oracles, the membership checking function for A and the membership checking oracle for A perp. What should we do with them? The idea is to use secret sharing. So our copy protection construction is quite simple. To copy protect F, each oracle checks, we have 2 oracles, O1 and O2. Each oracle checks if a part of the input is in A or in A perp respectively, and then gives out a secret share of the function F evaluated on X. So that is the first oracle. The input are two parts. It checks the second part, whether it's a valid non-zero vector in A. If so, it outputs a random function evaluation X. And for the second oracle, it checks the second part of the input, whether it's in A perp, and it outputs If it is so, it outputs the random function evaluation of x XORed with the actual function with copy protect. And so to evaluate the program, it's easy to see. So when we are given one copy of the state and access to these two oracles, we evaluate the program first by querying the oracle 1 in superposition using state A, and we measure the output register. And by the gentle measurement lemma, the remaining state is still good to use. So we do a QFT to the remaining state, and it becomes a perp. And we input that in superposition onto the second oracle, and give us another result. And we just XOR these results we obtain from the output register, and we would get fx. So I will explain the security proof on a very high level. So suppose an adversary is able to produce two programs, F prime and F prime prime, and both of these programs say they can successfully pass the test of the anti-piracy security game. Then we can do the reduction to break either of our underlying hard problems. In the first case, we say that we can extract a vector, a non-zero vector in A from the first part, from the quantum part of the first program. And in the second case, we can extract a vector in a perp from the second Pyro program. And if this event does not happen, we say that we must fall into the second case. And in the second case, we can use one of these programs to violate the unlearnability of them. So all these underlying problems are like either a fact or just provably hard. So they are not assumptions. And there is actually some subtlety in the security proof, but I will not go into details. Basically, in the extraction game, you have to be careful when the adversary could entangle his two Pyro programs. So then extraction on one state may disturb the other state, so that you can no longer extract. But you can use a delicate argument to get around such a cheating behavior. So okay, now we have an oracle construction. It's a classic oracle, good, but still very strong. So we wonder whether we can move to the actual cryptography world. Can we implement these constructions with more practical cryptography assumptions? Unfortunately, we do have a barrier in some sense. If we just want to remove the oracles directly and raise some assumptions and realize the same functionality that copy protects all functions, that's not possible. So a concurrent work by Ennis and LaPlaca shows that using this post-quantum assumption called learning with arrows, I believe it's quite famous, so most of you should have heard about it. And as well as the security of quantum FHE, of quantum fully homomorphic encryption. Yeah. There exists a class of unlearnable circuits that can be learned once given the copy protection program. So this is an impossibility result in the sense that we cannot build a copy protection program that the copy protects all unlearnable functions, because no matter what copy protection you do, once you give out a program that copy protects such a functionality built in this paper, then you can always learn the function and just recover the functionality. And this does not contradict our Oracle result, because the way they show the impossibility is that you have to homomorphically evaluate on your program, and because you cannot homomorphically run on a quantum or classical oracles. So this basically shows a separation between the Oracle world and the real world, whereas once you are given the real code of a program, you can do something weird that you cannot do with the oracles. Okay, so in the face of this barrier, we need to consider what are the next achievable things we can do. So the next achievable directions in removing oracles are twofold. So first, we can consider just weakening the security notions. So the security notion for copy protection is actually quite strong. So if you consider it, the adversary can basically do anything to produce any quantum state, and it doesn't have to follow any rules. You just run a universal circuit to check whether it computes correctly, and if they can succeed in that case, they're done. So we can probably consider weaker but meaningful security notions for copy protection, in which we can realize security more easily. And we will mention this direction at the end. And the second direction is we don't relax our security notions because we think it's a good one. But we need to consider smaller classes of functions to copy protect. Since we cannot give a general scheme that copy protects everything, we can still give specific constructions for copy protection or of specific interesting functions, such as some cryptographic functionalities. And in the rest of the talk, I will focus on the second direction. So now it comes to our second topic today, copy protecting signature, decryption, and the pseudo-random functions without oracles. And this is the main result in this paper. And these functionalities, they were all known to be copy protectable with only classical oracles in our previous paper. I will mostly focus on the signature token scheme due to limitation of time. So we call this notion as signature token. It can be viewed as a basic copy protection for signatures that where the functionality of signing is also one time. And it consists of the following algorithms. So it has a generation algorithm that outputs a classical verification key and a secret key. And using this classical secret key, we can output a quantum token that you use to sign. Using the quantum token, and the message, for simplicity, we say the message is one bit. Well, we can just sign the message where the signature is supposed to be classical. And the verification algorithm takes in the verification key, message, and your claim signature and checks whether it's valid. The security guarantees that when given one copy of the quantum signing token and access to the classical verification key, it should not be able to, the adversary should not be able to produce two valid signatures on different messages. And here it's just that it should not be able to produce signatures for 0 and for 1 at the same time. So we start with the subspace state again. Now we just give one copy of the state to the adversary and the membership oracles for A and A perp. If you remember, we say that the adversary is not supposed to find two vectors in A and A perp. And Bendiv and Sata's 2016 paper used this property to build the first tokenized signature scheme. And these two vectors will just correspond to different signatures. However, the scheme is still in the oracle model. So how do we go from oracles to the plain model? As we said, we have this tool called virtual black box of classification, which just says it's different, no different from an oracle. So it doesn't really make much a difference if we just move to VBB. So we want some weaker assumptions. Instead, we use a primitive called IO, short for indistinguishability obfuscation. The definition of IO says that if we put two functionally equivalent, but probably with different circuits that look different, implementations look different, programs P0 and P1. Here it should be 0 and 1. And we obfuscate these two programs with IO, and the adversary should not be able to tell between these two obfuscated programs. And this notion is widely believed to be constructible. There are some recent progress building it from relatively reliable assumptions, and there are even some post-quantum candidate constructions. In general, I/O is very useful and powerful in building classical crypto tools. And for quantum, it's also very useful. So Jiahui in 2009 showed that using I/O, we can instantiate the public key quantum money scheme based on the hidden subspace. Using I/O, we can build something called subspace hiding obfuscation. And such subspace hiding obfuscation can replace the subspace membership oracles in the quantum money. So we want to do the same thing. However, it does not apply to our case directly. Jiahui subspace hiding obfuscator is good enough to build quantum money, but not secure enough for our purpose. The fact is that the property we require is actually a stronger property than the property required for the money scheme. In the money scheme, the adversary has to produce two states that are exactly uniform, almost exactly the uniform superpositions of vectors in A. It could allow some errors, but in our case, it's different. What the adversary has to produce are just purely classical. They just have to produce two vectors. So in order to use I/O, we found that it's in fact easier to work with an extension of subspace states we call co-Z states. And this notion was also brought up by Vidic and Jen in a paper at I think Crypto 2020. So subspace states are also can be viewed as quantum one-time padded. Co-Z states can be viewed as quantum one-time padded subspace states. We select random strings S and S prime. We shift the subspace state by S in the standard basis and shift it by S prime in the Hadamard basis. And now we get to a state that's shifted by these two secrets. I will not go into details why this state is easier to use, but the high-level intuition is that basically now instead of just finding any vectors in A and A perp, you actually also need to find out about S and S prime. And using co-Z states, we can get the previous unclonable security guarantee, but under I/O instead of oracles. Now we just replace the membership oracles with membership checking programs built from I/O for the co-Z. Next, we can construct signature tokens without oracles. This can be seen as a certain copy protection for the signatures functionality that is also one-time. Here, the co-Z state will become a signature token, and the verification keys are just the co-Z membership obfuscators. And clearly, now the signatures, signature for 0 correspond to just finding a vector in the co-Z A plus S, and the signature for 1 corresponds to finding a vector in the co-Z A per plus S prime. And by the other, we could show such a problem is hard, and that would just directly imply the security of the signature token scheme. Next, we quickly go through copy protecting decryption, which is the second main result in this paper. So using another stronger property of co-Z states, which we call monogamy of entanglement, we can obtain a public key encryption scheme where the quantum decryption keys cannot be copied. So in the security game, we give out this quantum secret key, just one copy, along with its corresponding classical public keys to the adversary. The adversary splits the quantum key, and later on, we just sample prepare two ciphertexts, encrypt two ciphertexts using the corresponding public key here, and feed them to the two Pyro programs, and we ask them to decrypt. And the security says that they are not supposed to decrypt successfully at the same time. And then based on this decryption copy protection scheme, we can then again obtain copy protection for pseudo-random functions. And this is based on some I/O tricks by Jiahui 2014 papers, how to use I/O. Let's just take a look at this chart again. So now we know that we have classical oracle to copy protect all unlearnable functions. However, that can't really be realized in the real world because there is this impossibility results that says there exists some contrived functionality that you can never copy protect, even though it's unlearnable. So that is indeed the separation between the oracle world and the real world. But in the real world, we don't really care about copy protecting such contrived functionalities that are not copy protectable. So we just go ahead and copy protect functions that where we can build specific copy protection schemes for them. So for example, signatures, decryption, and pseudo-random functions. These are all very important notions and meaningful for copy protecting, because just imagine any software where this cryptography functionality is like one part of the software, and and sometimes copy protecting this cryptography component just leads to probably copy protecting the entire software entity in some sense, because if you are not able to go through this cryptography part, you are probably not be able to use the entire functionality at all. And there's also another class of functions called point functions. So basically, point function is just a function that has one piece of, for example, a secret n-bit string that's embedded in the functionality. And if you hit that secret string on your input, then you would get out. You would pass like a certain validity check. You would get output 1, or you would get a secret message. And basically, this one n-bit string is the information you want to copy protect. And it also has this extension to a function called compute and compare, which can be viewed as a certain kind of evasive functions. But you can copy protect them nevertheless using the similar idea, because the most important part of these functions is just the most important and unpredictable part of these functions, that you have to hide this secret n-bit string. And this can be done in the quantum random oracle model. So it was firstly the scheme was obtained in this paper, I think by Andrea Cladangelo, Christian Margins, and Alex Paramba. And at that time, they tried to build it from unclonable encryption, which is another notion I will briefly mention later. And but they could not achieve very good security. And later on, achieved good security was achieved in a very recent paper. Also very relevant using basically, I think it's the same construction, but they achieve a better security because they can achieve better security with unclonable encryption. So there are also many more interesting unclonable cryptography primitives out there. The first one is secure software leasing or copy detection. So they are a weaker version of copy protection. So here, here's the high-level idea of this notion. The pirate can do anything malicious, but the evaluators who run the pirate programs are honest and will follow specific procedures to run them. And this basically guarantees that when you evaluate the programs, when you test the adversary programs, you are not using a universal circuit to test them, but instead you are using like the authentic procedures specified by the vendors on how to run the program. So this largely limits what the adversary can do, and you would be able to be able to get easier security proofs. However, this notion still suffers from the general impossibility result. But the good thing is it's easier to do security proofs with such a notion. Whereas in copy protection, it's much more annoying to do reductions. Sorry, there's one other paper I think I mistyped and forgot to put in there. I think it's a paper on also on secure software leasing for point functions and information theoretically, and it should be it was published last year in TCC, and okay, and then there are two other notions that are quite popular recently. That is unclonable encryption and certified deletion. So here the ciphertext is here we have an encryption scheme where the ciphertext is an unclonable state. And what you want is that you don't want the adversary to split the ciphertext so that later on two parties can decrypt at the same time. And for certified deletion, you additionally want the adversary to produce a certificate that they have measured or say destroyed the state that's previously sent to them. So it's giving a kind of everlasting security. And that's basically everything for today. Thank you. Let me know if you have any questions.
Yeah, thank you. Nice talk. Yeah, so we have some time for like 2 or 3 questions. So are there any questions?
Are there any questions on site or online?
Okay. Yeah, actually, I have some questions. So right now you are talking about copy protection or unclonable for classical functionality. So have anyone think about like I want to copy protect some like quantum functionality, and what's the challenge if I want to copy protect a quantum function? Yeah.
Okay, I see. So I think there are a few challenges. So because so in classical functionality, I think one unless the function is like very simple, like a point function, what we usually need for a start is we need to obfuscate the functionality. So that's why classically we already rely on strong tools such as IO and even VBB if we want to copy protect everything. And so what we say that in the quantum world, I believe we can certainly copy protect some functionalities if we assume there is obfuscation for quantum circuits. And I believe we could also copy protect some simpler functionalities. For example, if we define a quantum point function by saying the function is just a projection onto some random state you want to hide, and I think that's probably doable without too many strong assumptions. But I'm not sure. So I've thought about the problem for a while, but haven't got like something provably secure. And the other thing, is that if you do copy protection, you probably want your scheme to be reusable. So if you have a quantum functionality, it's very so unless the functionality is like a channel that's pseudo deterministic, right? If you always get a certain output once on some input, but if it's highly probabilistic, you probably just destroy your program after one round. So that's also like some limitation, and you probably want to give out like a polynomial number of copies, like like a bounded polynomial of copies, so that the user can run for these many times, right? So that's the basic two things, right?
Also, regarding that, just have another question just raised, because you mentioned the one-time signature scheme, right, by, sorry, I forget whom. So is that one also need to be reusable? I mean, I can use a token like polynomial many times to do a signature?
Right, that scheme is indeed not reusable, and like this security notion, basically it wants the signing token to be not reusable. It just wants the adversary to only sign one signature. Yeah, right. Basically, if you the thing is the way you produce signatures honestly is just by measuring your state in the corresponding basis you want to sign. And when you verify the signatures, we're sort of assuming a certain classical communication channel between the verifier and, or say the verifier always measures your signature when you give it to him. So that they cannot say I can just coherently sign signatures and do it for many times. So this is what we want for the signature scheme. But we can indeed make another different signature scheme that is reusable for many times. That's a follow-up work that we haven't put out yet, and that would be actually we can obtain it by using the PRFs. So using the copy protection for PRF. So here the copy protection for decryption and PRFs, they are many times reusable, and we can basically a way to realize signature schemes classically is basically just ask the signing algorithm is actually an evaluation of the PRF, right, on the message you want to sign. So your signing key is like the evaluation key for PRF, and it's secret. And the verification procedure is like an IO, like checks whether your PRF evaluation is correct. So we can realize such a copy protection for such a signature scheme, right? And that scheme is many times reusable.
I see. Sounds like using one-way function. Okay, PRF. I see.
Right. That's actually it still requires IO, but it's But otherwise, it's using just QRF and one-way functions, right?
Okay. Oh, yeah. So any more questions?
Any questions?
Okay. So if no, then let's thanks Jiahui for a nice talk again. Yeah.
Thanks.
Thank you, Jiahui, for the presentation. Also, I would like to thank the session chair as well, Jiahui Jia, for moderating this session. Thank you.
Thank you.
And now we will take a short break. Please come back at 10 o'clock for our next session. Thank you.